let's see another example of a phase portrait. Phase portrait. And let's consider the system dx dt equal 4x plus y and dy dt equal negative 5x minus 2y. In this case, the matrix of the system is 4, 1, negative 5, negative 2. To compute the eigenvalues, we compute the trace. The trace of A is 2, 4 plus negative 2 is 2, and the determinant of A, it would be negative 8 minus negative 5. Negative 8 minus negative 5 is negative 8 plus 5. That means it's negative 3. That means that the characteristic equation is lambda squared minus 2 lambda minus 3 equals 0. And then let's find the eigenvalues. Is lambda minus lambda plus equals 0. And then we have negative 3 and positive 1. That means that lambda equal 3 or lambda equal negative 1. To compute this eigenvector, we solve this system. A, which is 4 minus lambda, 4 minus 3 times x plus 1 times y equals 0. And the other one is negative 5x plus negative 2 minus 3 times y equals 0. If everything is okay, these two equations are supposed to be essentially the same. Let's see, 4 minus 3 is 1. That means x plus y equals 0. And here we have negative 5x minus 5y equals 0. We check, they are essentially the same. And one solution, we can pick x to be equal 1 and y negative 1. 1 and negative 1 will work. That means that we have one eigenvector, 1, negative 1. To compute the other eigenvector for lambda equal negative 1, we solve this system of equations. We do 4 minus lambda. 4 minus negative 1 is 4 plus 1 times x plus 1 times y equals 0. Negative 5x plus negative 2 minus lambda plus 1 times y equals 0. If everything is okay, these two equations are supposed to be essentially the same. 5x plus y equals 0. And the other one is negative 5x minus y equals 0. And one possible solution is x equal 1 and y equal negative 5. X equal 1 and y equal negative 5 satisfy both equations, and then we have our second eigenvector. Now let's do the phase portrait. We have, we do the Cartesian plane. We know that this 0, 0 is a solution, is an orbit on its own. For lambda equal 3, we have this eigenvector, 1 and negative 1, and then we draw the line. In that line, we label it lambda equal 3, and the other line is 1, negative 5. 1 and negative 5 is like here. Let's do that line. And this line goes with lambda equal negative 1. Let's erase the axes because they are not part of the orbits. And since this lambda, remember that this it has to be viewed not as a line but as two semilines. Since for this semiline the lambda is negative, the arrow goes toward the origin. And since in this semiline the lambda is positive, then the arrow goes away from the origin. And in each one of these quadrants, 1, 2, 3, 4, we're supposed to do something like a hyperbola. Remember that a hyperbola is something that goes like 1 over x. It has two asymptotes. Here, this is one of the asymptotes. And then it will go close to the other line to be like another asymptote. I haven't started here. I see like this. This here, we have this. In this quadrant, the hyperbola is almost like it has this semiline as an asymptote, and then the other semiline also as an asymptote. Here we have the same, and here we have the same. Let's see the directions. Notice that for this type of hyperbola, the semiline goes toward the origin and this one goes away. Then the direction of this is going down. In this case, this semiline goes toward the origin, this goes away. Then the direction in this orbit should be like this. For this semiline goes toward the origin, this goes away. Then the direction goes like that. And for this one, this goes toward the origin, this goes away, then the direction goes like this. Remember that this equilibrium point is called a saddle. Then we have an example of a saddle. Okay, that's it.